All right, welcome to Dev Summit 2020. Daniel and I are going to be talking about the process of performing geographic feature engineering. So today we'll be talking to you by myself, Joel McCune, and also Daniel Wilson will be joining me. So what we're really focusing on is the concept of how we marry machine learning with doing GIS analysis. We're going to start off by talking about a couple of different concepts with machine learning to frame the discussion. And from there, then Daniel and I are going to talk about a few things we've been working on that'll hopefully paint a picture of how this can all work together. So when we're talking about machine learning, we really first need to investigate this idea of a feature, what feature engineering is, and then also the concept of how this all fits together with geographic feature engineering.
So when is a machine learning model the right model to use? If we're applying geographic feature engineering, we're assuming at this point that the machine learning model is the correct model to use. George Box, the statistician, has been quoted as saying, "All models are wrong, but some are useful." That's precisely when you would use a machine learning model, when it's useful. Only you'll be able to determine that, and Joel will go into a few reasons why you might want to consider using a machine learning model in your analysis.
So what Daniel was talking about, that some models can be useful, ultimately this begs the question of why do we even want to use machine learning in the first place? One of the major reasons is machine learning is an inherently data-driven approach. It allows you to agnostically, without any bias, take the data and understand the relationship of different quantitative metrics to whatever outcome you are trying to predict, to be able to understand. And this, while it allows you to have a very agnostic approach, it also scales extremely well. That's what we're talking about with 11 factors. You and I. The human brain that we have is capable of conceptualizing generally around 7, but up to about 11 potential causal factors related to any outcome that we're trying to forecast. Utilizing machine learning allows us to overcome this inherent limitation of being human. It allows us to scale really only with the limitation of the amount of compute that we have available, which, given the days of now that we have so much cloud computing available, allows us to access tremendous computational power, effectively allowing us to scale out our ability to understand the relationship with almost an infinite number of factors that we get in. What this allows us to do is overcome the challenge that is so frequent of drowning in data. And it allows us to do it in a way that is incredibly data agnostic, in that we can test as many inputs as we possibly want and allow the process to tell us what's relevant and in what magnitudes. Before we get into this, though, this talk is about geographic feature engineering. This is pulling together the disciplines of GIS and data science, and in both of these have the term feature defined in a very different way, which makes this kind of a loaded term. When we look at the realm of GIS, a feature is the representation of a real-world object on a map. Typically, we think of this in terms of what is referred to as simple features: points, lines, and polygons. We have some information that's associated with them. We put that in the attribute table. But ultimately, this information related to things that are somewhere on the Earth, this is what we think of as a GIS feature. However, in the realm of data science, a feature has a somewhat different meaning. It's a measurable property or characteristic of a phenomenon being observed. Really, it's just a quantitative scalar measure. So when we think of this and we visualize this, we get into feature engineering, and this is how we create these data science features. We use some sort of domain knowledge to be able to quantify entities, and we pull this out of raw data using a number of different data mining techniques, And what this does is this gives us accurate measures that improves the performance of machine learning algorithms. It gives us something to train a model with. When we talk about features, really all we're talking about is creating these tables of nothing but numbers. And so what we can do with this is we can apply geography to create accurate measures of Tobler's law. We can create accurate measures of how everything is related to everything else, but near things are more related than distant things. And when we quantify this, commonly it's easy just to do it in straight line distance. So if we have 3 different points and we want to know how to get to the middle point, we can see that if we use straight line distance, the southern point appears to be almost 1/3 of the distance from the northern point. However, in reality, it's somewhat different. The southern point is almost 20 miles away, while the northern point is only about 5. Obviously, this is because of geographic barriers. We are quantifying geography in a way that can be used for machine learning. But ultimately, as geographers, we understand that distance isn't always the most accurate measure of proximity. Because in fact, you have to drive there, and if you're driving there, what really matters is how long it takes. And in this case, this changes the relationship even again, so that by applying our domain knowledge of geography, we're able to create quantitative measures, and these quantitative measures can be included as part of our machine learning. So when we start thinking about this, if we're going to call this geographic feature engineering, we're applying our domain knowledge by using GIS and data science methodologies together so that we can create quantitative measures of geographic relationships and phenomena and use these as part of machine learning model development.
For the remainder of this presentation, we are going to discuss 3 categories of geographic feature engineering and motivate them with some concrete examples from some projects that we have worked on. These 3 categories are enrichment, context, and geometry. Enrichment is the act of creating features by extracting attributes from a different data source. That data source could be a related table, such as through a key relationship, or it could be enriching the geometry with attributes from something that is overlapping with it, such as demographics or other values. Context is the act of creating features by examining how the geometry or its attributes relate to other data. Imagine you're driving down the road. Off to your left is a steep incline up a hill, and to your right is a steep drop-off. That's not as simple as just enriching the point on the road with the fact that there is a slope to your left and a drop-off to your right. You could, but you could also create other features that take into account the larger context. The last category we're going to discuss is geometry. Imagine you're driving down that same road, but now that road is very, very curvy. What if we wanted to take that geometry and capture that curvature as an attribute? That's something we can do by computational geometry, actually using the geometry of the road itself. Now we're going to talk about geographic feature engineering in more concrete terms. Specifically, we're going to talk about a couple example projects. The first is car accident prediction, and the second is customer-centric analysis, basically applying geospatial AI to retail site selection. So first up, car accident prediction. Really, when I say car accident prediction, I mean car accident risk prediction. That is, we're not ever going to be able to create a machine learning model that can predict every car accident. They're a random event. But what we can do is apply geography and machine learning together to create a model that can estimate the car accident risk on 2 different pairs of roads. Imagine you're looking at this road here, and we want to estimate the crash risk at every point along the road. If I look at these 2 points, can you tell me which one has a higher chance of an accident? Well, enriching these 2 points with various sets of data might allow us to build a machine learning model. Once we have a machine learning model, we can run that on every point along the road and estimate the risk at every milepost. To do this, we need features. so that the model can compare these points. Let's give some concrete examples of geographic feature engineering by taking a quick tour of Colorado. In order to make a predictive model, we need to determine what factors we should consider in the first place. How would these fit into a predictive model? For car accidents, we're going to roughly break this into a few different categories. Human factors, basically anything related to humankind's influence on car accidents. It's a very long list. Physical factors, points that are or properties that are intrinsic to a point on the road. And environmental factors, basically how are things changing? What are the conditions? Things like weather. The first of the human factors that we're going to talk about is population density. Car accidents, it should come as no surprise, happen in areas where people tend to be. We can look at variables from Esri demographics, such as population density, and that can help augment existing data sources that may be available, such as annual average daily traffic from a local or state Department of Transportation. But what if we're looking at other attributes in our model? Maybe we want to model the risk of bicycle-related accidents. In that case, in addition to population density, it might be helpful to know what is the number of people that bike to work. This is a variable that we have available through the Esri demographics data, and we can use that to help enrich our model. There are numerous possible data sources to consider. For a model like this, can you think of more? Let's look at a specific road. If we look at this road out of context, we might be able to discover some interesting things from the attribute table. Speed limit, the average traffic counts, number of lanes, other information such as that. Really, the list goes on, but when you're looking at this road with no other information behind it, curvature is the first variable that would come to mind. You can see that there's two sharp curves in this road, and maybe that adds a hazard to this road. But can you tell the difference between this road and this one right here? Well, clearly they're different roads, but they're both just about as curvy as each other. They have nearly identical properties, such as the speed limit or lane count. It's really hard to say which one's more hazardous until you include its geographic context. Now the story gets a whole lot more interesting. This road, as we can see, is running through the mountains. We can talk about things like the road slope, elevation, in addition to its curvature. But let's look at that first road again. That first road is going through the middle of the countryside. Very, very few people living in this area, and it's clear that the accident risk comparing these two roads is not going to be the same. So what we need to do is create new features that take into account context, geometry, and enrichment to improve this predictive model. But when we actually say curvature, what do we mean? This is going to be our first example of a geometric calculation. In this case, we are using the polyline geometry from the road to estimate the curve radius. One way to do that is to use the field calculation tool and some simple trigonometry to estimate the radius of a circle that would touch the road at a few different successive points. Places along the road, such as these sharp hairpins here, would have a smaller circle because they are more sharply curved, and areas such as this would have a larger radius when they're not as curved. Let's look at another example. This is one of my favorite locations in Colorado, the mountain town of Ouray. Clearly, this is a very curvy road, but what else can we say about it? I think we're missing out on the context without looking at its surrounding geography. Not only is this a beautiful view, but there's more content that we can use for feature engineering. Referencing the issue I mentioned earlier about steep drop-offs. Imagine you're driving down that road that's off in the distance. There's a steep mountain road, or it's a steep mountain road. There are sharp inclines to the left of the road and steep drop-offs to the right. Falling rocks could provide road hazards, and that's something we might want to include in a model. But if we're using a digital terrain model, we can use our imagination and add new features. We can also talk about visibility. It's a curvy mountain winding road through the mountains. chances are there's going to be places where we have blind corners or other potential road hazards. We're clearly missing out on the greater context if we're just looking at the roads themselves or ignoring dynamic conditions like time of day. Clearly, this road would be very different driving in the day than it would be at nighttime. Let's look at a completely different area. This is the I-25 corridor in downtown Denver. Around this area, we see some of the largest count of accidents, and sometimes it's really easy when looking at a map like this to miss out on the greater context. In this case, this is a highway going through one of the most populated areas in Denver, probably the most populated area in Denver. If we add in 3D content, such as these buildings models, we can calculate additional features to model visual obstructions or challenging driving situations. Let's pause for a second right here. First, we've included these 3D models from the Denver Open Data Catalog, and you can see that when we add them in, the roads are very, very different. When you just look at the geometries themselves or even the attributes, an area that is near all of the tall buildings in the center of downtown could look very similar to one that's in the suburbs, but adding in all of this additional information makes our model more accurate. Consider the time of day. Imagine you're driving through the city. Now, most of the time, these tall buildings are going to block the sun, but what happens if you turn a corner? There's no longer a building blocking your viewpoint. The sun is setting over the Rocky Mountains, and all of a sudden you're blinded by the sun. This obviously is going to create some sort of driving hazard, and it's impossible to model that without taking into account the 3D context, such as the terrain and these 3D building models. In a suburban environment, like I referenced before, things are going to be very different if we have different sizes of buildings, different street layouts. But imagine you're at this point right here. So we're in downtown Denver, we're driving along the road. What we would like is for our model to be able to capture what it would be like to drive down this road. ArcGIS allows us to use abstractions such as building and terrain to estimate what points are blocked to the driver. We can use this to calculate new features, such as the mean field of view of a driver, the dominant visible direction, or the density of visual obstructions. Really, you can use your imagination again and construct different features based on what it is you're trying to model. This can provide the model a brand new perspective. Now we're not only taking into account one attribute or even a few, but we can calculate dozens of attributes off of dozens of different data sources and bring a lot more power to our predictive model.
Following on Daniel's excellent example, now we can take a look at customer-centric analysis. What we're really referring to here is retail performance. We want to be able to forecast and understand the relationship of a customer to a retail brand. Typically, what we're interested in is forecasting retail performance so we can understand either A, how we can better engage with the customer, or B, where are viable locations for new store locations. Specifically, we're looking for either headroom or green spaces, so places we can expand and densify within an existing market or new markets that we can expand into. The way that we do this is slightly different than has conventionally been done. We're really looking at this, as we said, from the customer's perspective. And in this case, what we're using is block groups. So for instance, the red area that's the origin for all these lines you're seeing on the screen, that is a census block group. We use this level of geography because everybody can safely be assumed to be demographically homogeneous within this area. What we're really saying is everybody in this area is the same. And based on that, what we can do is then evaluate the relationship of the customer at this level to the surrounding retail landscape. And the first step that we do in this is we calculate from this origin geography, the block group, the distance, or rather I should say the proximity, to the 6 closest brand stores. And we do that not just for one single block group. Obviously, we do it for every single block group in our study area. as you can well imagine, it doesn't take long before this is a lot of data we have created very, very quickly, because we now understand the geographic relationship of every single block group to the nearest 6 brand locations in our study area. But ultimately, like we said, we don't want to understand just the relationship of the customer to our brand. We want to understand the relationship of the customer to the retail landscape for forecasting performance against our brand. So that requires that we include competitors as well. So not only do we calculate the distance to the nearest 6 brand stores that belong to us, we also consider the distance from the customer to the nearest 6 competitor locations as well. And we do this, again, not just for one. Obviously, we do it for every single block group in our study area. What this allows us to do is this allows our modeling effort to quantitatively be able to take into consideration not only competition, but also cannibalization, competition between our own stores. And this is natively part of it because what we do is we calculate this not only for one metric. We do it for drive distance, obviously, but we also include various metrics of drive time. Normal drive time, morning and rush hour drive time, weekday drive time, weekend drive time. This allows us to be able to have a very data-driven approach to allow the process of modeling and feature selection to be able to tell us what matters and in what magnitudes. Once we're done with this, we can, as part of our modeling effort rather, we want to combine this with our demographics. We want to include up to, as we said, we can grab 5,800 demographic variables just out of the Esri data alone. Frequently, our customers that we work with doing this bring a lot of their own data to the table as well. And we combine this, again, with all this demographic data and all of these proximity metrics to be able to then perform the feature engineering necessary to do modeling of the customer's relationship with the surrounding retail landscape. This ultimately can allow us to forecast performance not only for existing stores, but also we can evaluate hypotheticals. Say, for instance, we were to put a store in this new area we're looking at below and place it in the center of that area. We then can combine that with the demographics we already know about the customer, and given this hypothetical new store location that we potentially could add, we then run our model that we've created, and this allows us to evaluate what would be the performance of putting a new store in this location. And it tells us not only the effects it's going to have for how the new hypothetical location may perform, it also will tell us the effects it potentially can have on the existing store locations, the cannibalization effect that it will have on the surrounding stores in this retail marketplace. Or, well, retail landscape, rather, is the word I should be using. What's useful about this, since we have a repeatable model we can now use, we can take this and not only do it for 1 or 2 locations, but we can create just a regularized grid across our market, and then we can create a map that shows us where opportunity exists to densify within an existing market. This shows us where headroom exists in the market and where we should be looking at for expansion efforts. So based on that, what you've seen here is a couple of different examples of geographic feature engineering. Before that, we even investigated the idea of what really is even a feature. And so one of the most useful things about this is, based on this, by combining geographic and artificial intelligence, we pull together to perform geographic feature engineering for machine learning, where we use GIS along with data science, and this allows us to create quantitative measures of geographic relationships for machine learning model development. The important thing with this, by combining these two disciplines and doing it well, what you are doing is you are achieving insights that you wouldn't be able to get with either one of the respective disciplines of just data science or just GIS alone. And what Daniel and I have started to realize here by our combined efforts on this team is the incredible power that really comes from combining the best of these two disciplines. So hopefully we've helped you illuminate some of the ideas that may come out of this, and please feel free to reach out to us if you have any questions. Other than that, thank you for watching, and thank you for attending one of the most unique developer summits that we've had thus far.